Mechatronics is a fascinating field that blends mechanics, electronics, computer technology, and control engineering to create smarter, more efficient systems. Originating in Japan during the 1970s, the term was first coined by Mr. Tetsuro Mori, a senior engineer at Yaskawa. The essence of mechatronics lies in its synergy, combining multiple disciplines to produce systems that are simpler, more reliable, and cost-effective. This introduction sets the stage for understanding how mechatronics has revolutionized industries by automating processes and enhancing product quality. As we move forward, we'll explore the key advantages and challenges associated with mechatronics. The concept of mechatronics emerged in Japan in the late 1960s, with Mr. Tetsuro Mori of Yaskawa introducing the term. Initially, it described the integration of electronics and computer technology into mechanical systems, paving the way for automated control and smarter machines. Over time, mechatronics evolved to encompass a broader range of technologies, including sensors, actuators, and advanced control units. This historical perspective helps us appreciate how mechatronics became a cornerstone of modern engineering, influencing everything from manufacturing to robotics. Mechatronics can be defined as the application of electronics and computer technology to control the motions of mechanical systems. It represents a synergistic combination of mechanics, electrical engineering, electronics, computer science, and control systems. By merging these fields, mechatronics enables the creation of systems that are not only efficient but also adaptable and reliable. This multidisciplinary approach is what sets mechatronics apart from traditional engineering, allowing for innovative solutions in automation and intelligent design. Mechatronics offers several compelling advantages. Automated machines can operate continuously, maximizing utilization and productivity. The reduction in human labor and fewer machine parts lead to lower operating and maintenance costs. Compact designs save space, and the use of automatic systems ensures uniform product quality. Flexibility is another key benefit, as mechatronics systems can be easily modified or redesigned. Additionally, smart machines with self-correcting sensory and feedback systems help minimize waste and improve efficiency. These advantages make mechatronics a preferred choice in many industries. Despite its many benefits, mechatronics also presents some challenges. The initial cost of implementing a mechatronic system can be high, requiring significant investment. Designers and engineers must possess knowledge across multiple fields, making the process complex. Specific problems often require highly qualified professionals to address them. Furthermore, retrofitting existing systems with mechatronics technology can be expensive and difficult. Understanding these disadvantages is crucial for making informed decisions about adopting mechatronics in various applications. Additional systems rely heavily on mechanical components such as levers, gears, and cams to perform tasks. In contrast, mechatronic systems integrate electronics with mechanical parts, resulting in greater flexibility and accuracy. Traditional mechanisms are often more complicated and involve more moving parts, while mechatronics simplifies design and reduces the number of components. Automation replaces manual control, making mechatronic systems more efficient and reliable. This comparison highlights the transformative impact of mechatronics on engineering and everyday devices. A clear example of the shift from traditional to mechatronic systems is seen in alarm clocks. Traditional mechanical alarm clocks use gears and springs, requiring manual setup and adjustment. Mechatronic alarm clocks, on the other hand, combine electronics and computer technology, enabling automatic control and enhanced features. This evolution demonstrates how mechatronics improves everyday objects, making them more user-friendly, accurate, and reliable. The integration of sensors and microcontrollers allows for smarter operation and customization. Comparing traditional and mechatronic systems, several differences stand out. Traditional systems are less flexible, less accurate, and involve more complicated mechanisms with numerous moving parts. They are controlled manually and require more components. Mechatronic systems, in contrast, are more flexible, accurate, and have simpler designs with fewer parts. They are controlled automatically, making them easier to maintain and operate. This comparison underscores the advantages of adopting mechatronics in modern engineering. Mechatronic system is composed of four main elements: sensors, control units, actuators, and mechanical components. Sensors detect system parameters like temperature or pressure. The control unit, often a microcontroller or computer, processes sensor input and makes decisions based on programmed instructions. Actuators produce motion or actions such as motors or valves. The mechanical system ties everything together, forming a complete unit like a robot or washing machine. Understanding these elements is key to grasping how mechatronic systems function. Sensors are vital components in mechatronic systems, responsible for detecting physical parameters such as temperature, pressure, displacement, and force. Examples include thermocouples, accelerometers, and gravity sensors. These devices convert physical inputs into electrical signals, which are then processed by the control unit. Sensors enable systems to monitor their environment and respond intelligently, forming the foundation for automation and feedback control. Their role is essential in ensuring accuracy and reliability in mechatronic applications. Control unit in a mechatronic system acts as the brain, making decisions based on sensor input and programmed instructions. It can be a microcontroller, computer, electronic circuit, or PLC. By processing data from sensors, the control unit determines the appropriate actions for actuators. This decision-making capability allows for precise control and automation, adapting to changing conditions and ensuring optimal performance. The control unit is central to the intelligence of mechatronic systems. Actuators are the components that produce motion or cause actions in a mechatronic system. Examples include solenoids, DC motors, stepper motors, servo motors, hydraulic and pneumatic cylinders, and heaters. Actuators receive signals from the control unit and execute tasks such as moving parts, opening valves, or heating elements. Their ability to convert electrical signals into physical actions is what enables mechatronic systems to interact with the real world and perform complex operations. Mechanical system is the physical arrangement of components that forms the core of a mechatronic device. Examples include robots, autonomous guided vehicles, vehicle engines, and washing machines. These systems are designed to work as a unified whole, with sensors, control units, and actuators integrated seamlessly. The mechanical structure provides the foundation for movement and operation, while the electronic and computer elements add intelligence and automation. Practical example of a mechatronic system is the automatic tap. Here, a proximity sensor detects the presence of a hand and sends a signal to the control unit, typically a microcontroller. The microcontroller processes the input and decides whether to activate the tap. A solenoid valve acts as the actuator, controlling the flow of water. This system demonstrates how sensors, control units, and actuators work together to automate everyday tasks, improving convenience and hygiene. Mechatronic systems come in various forms, each tailored to specific applications. Examples include measurement systems, control systems, and automated devices. Measurement systems use sensors to monitor physical parameters, while control systems manage variables and sequences of events. Automated devices combine these elements to perform tasks with minimal human intervention. Understanding the different types of mechatronic systems helps us appreciate their versatility and impact across industries. Measurement systems in mechatronics use sensors to convert physical inputs, such as temperature or displacement, into electrical outputs like voltage. The data processing unit receives this input and processes it according to programmed instructions, often performing signal conditioning. The data presentation unit or recorder then displays or records the measured parameter in the desired format. An example is the digital thermometer, which we'll explore in detail later. Control systems are designed to manage variables, sequences of events, or determine whether an event occurs. Examples include steering control in automobiles, room air conditioning, automatic sensing doors, and washing machines. These systems use sensors and control units to monitor conditions and make decisions, ensuring optimal performance and safety. Control systems are fundamental to automation, enabling machines to operate independently and efficiently. Open-loop control systems operate without feedback, meaning the control action is based solely on the reference input. The controller does not check the output condition, so errors cannot be self-corrected. These systems are simple in construction, economical, and easy to maintain, but they are less accurate and reliable. Any changes in system components must be addressed manually. An example is the manual cloth dryer, where the operator sets the timer without checking if the clothes are dry. Consider a cloth dryer as an open-loop system. The operator manually sets the timer based on the wetness of the clothes. After the set time, the dryer stops regardless of whether the clothes are actually dry. There is no feedback mechanism to check the dryness, making the system dependent on human judgment. This example illustrates the limitations of open-loop systems, highlighting the need for more accurate and automated solutions. Closed-loop control systems use feedback to monitor output and adjust control actions accordingly. The controller considers both the reference input and feedback from sensors, enabling automatic correction of errors. These systems are highly accurate and can be automated, but they are more expensive and complex to design and maintain. Closed-loop systems are essential for applications requiring precision and reliability, such as automated cloth dryers that sense dryness and adjust operation. A closed-loop cloth dryer, the user specifies the desired dryness level. A sensor measures the dryness of the clothes and provides feedback to the controller. The controller compares the sensor output with the required dryness and adjusts the operation accordingly. This feedback mechanism ensures accurate results and reduces the need for manual intervention. Closed-loop systems demonstrate the power of automation and intelligent control in mechatronics. Pairing open and closed-loop systems reveals key differences. Open-loop systems lack feedback, are less accurate, and rely on human judgment. They are easier to design and build but cannot automatically correct errors. Closed-loop systems include feedback elements, are more accurate, and adjust control actions based on output and sensor input. They are more complex but offer greater reliability and automation. This comparison highlights the importance of feedback in modern mechatronic systems. Mechatronics is widely used in home appliances such as washing machines, air conditioners, ovens, and dishwashers. These devices incorporate sensors, control units, and actuators to automate processes, improve efficiency, and ensure consistent quality. Automation in home appliances reduces manual effort and enhances user convenience, making everyday tasks simpler and more reliable. The integration of mechatronics has transformed the way we interact with household devices. Automobiles benefit greatly from mechatronics, with systems like airbag safety, anti-lock brakes, and automatic door locks. Sensors and control units monitor conditions and respond instantly to ensure safety and performance. Mechatronics enables advanced features such as adaptive cruise control and automated parking, making vehicles smarter and safer. The integration of electronics and mechanics in automobiles showcases the versatility and impact of mechatronics technology. Mechatronics is also prevalent in office equipment such as laser printers, photocopying machines, and fax machines. These devices use sensors and control units to automate tasks, improve speed, and enhance reliability. Automation in office equipment streamlines workflow, reduces errors, and increases productivity. The adoption of mechatronics in office environments demonstrates its ability to optimize routine operations and support modern business needs. Entertainment, mechatronics powers devices like autofocus cameras and video games with virtual reality. Sensors and control units enable responsive and immersive experiences, enhancing user interaction and enjoyment. Automation and intelligent control make entertainment devices more versatile and engaging. The use of mechatronics in entertainment highlights its role in creating innovative and interactive products. Robotics is a prime example of mechatronics in action. Robotic arms, humanoids, automatic guide vehicles, and welding robots all rely on sensors, control units, and actuators to perform complex tasks. Mechatronics enables robots to operate autonomously, adapt to changing environments, and execute precise movements. The integration of multiple technologies in robotics demonstrates the power and potential of mechatronics in advancing automation. Mechatronics has revolutionized the medical field with innovations like artificial arms and robotic surgery. Sensors and actuators enable precise control and movement, improving patient outcomes and expanding treatment possibilities. Automation in medical devices enhances accuracy and reliability, supporting complex procedures and rehabilitation. The application of mechatronics in healthcare underscores its importance in advancing medical technology. Mechatronics plays a crucial role in military operations, powering drones and automatic weapon systems. Sensors and control units enable real-time monitoring and response, enhancing safety and effectiveness. Automation in military devices allows for remote operation and precision targeting, reducing risks and improving mission outcomes. The integration of mechatronics in defense technology demonstrates its value in critical application. Digital thermometer is a classic example of a mechatronic measurement system. Temperature sensors such as thermocouples, RTDs, and thermistors detect temperature changes and produce electrical signals. These signals are conditioned and processed by a microcontroller, which converts them into temperature values. The result is displayed on an LCD screen, providing accurate and real-time measurements. This case study illustrates how mechatronics combines sensors, control units, and data presentation for practical applications. In an engine management system, a microprocessor receives input from various sensors and operates actuators to optimize engine performance. Sensors monitor engine speed, crankshaft position, spark timing, temperature, throttle position, and airflow. The microprocessor processes this data and controls actuators like spark plugs, throttle valves, and fuel injectors. This system ensures efficient combustion, power output, and fuel economy, demonstrating the complexity and effectiveness of mechatronics in automotive engineering. Engine management systems rely on several sensors: engine speed sensors for spark timing, crankshaft position sensors for piston location, spark timing sensors, engine temperature sensors for cold starts, throttle position sensors, and mass airflow sensors. These sensors provide critical data to the microprocessor, enabling precise control of combustion and engine operation. The integration of sensors in automotive systems highlights the importance of mechatronics in modern vehicles. Actuators in engine management systems include spark plugs, throttle valves, and fuel injectors. Spark plugs initiate combustion, throttle valves regulate air intake, and fuel injectors control fuel delivery. The microprocessor uses sensor data to operate these actuators, optimizing engine performance and efficiency. This coordinated control demonstrates the power of mechatronics in achieving precise and reliable operation in automotive systems. Automatic washing machines are a common example of mechatronic control systems. The microprocessor checks if the door is closed using a sensor, then operates a valve to fill the drum with water. Water level sensors provide feedback, allowing the microprocessor to switch off the valve when the desired level is reached. The main wash cycle involves heating water, rotating the drum, and emptying water, all controlled by sensors and actuators. This automation ensures efficient and thorough washing. During the per-wash cycle, the microprocessor ensures the door is closed before starting. It operates a valve to allow water into the drum, with a water level sensor providing feedback. Once the desired water level is reached, the valve is switched off. This sequence demonstrates the use of sensors and actuators to automate and optimize washing machine operation, reducing manual effort and improving performance. The main wash cycle, the microprocessor operates a switch to turn on the heater, heating the water. A temperature sensor monitors the water, allowing the microprocessor to switch off the heater when the required temperature is reached. The drum motor is then activated to rotate the drum for a preset time, with a speed sensor providing feedback. The discharge pump is operated to empty the water, ensuring thorough washing and rinsing. Rinse cycle involves a sequence of activities, allowing water in, operating the drum motor, and activating the pump to empty water. This cycle is repeated several times, with the drum motor switched to high speed for final rinsing. Automation in the rinse cycle ensures consistent and efficient cleaning, demonstrating the benefits of mechatronics in household appliances. Feedback mechanisms in washing machines, such as water level and speed sensors, enable precise control and automation. The microprocessor uses sensor data to adjust operations, ensuring optimal washing and rinsing. This feedback-driven approach reduces errors, improves efficiency, and enhances user convenience. Mechatronics transforms washing machines into intelligent devices capable of adapting to different conditions. Mechatronics is present in many aspects of daily life, from home appliances and automobiles to office equipment and entertainment devices. Its integration of sensors, control units, and actuators enables automation, improves efficiency, and enhances user experience. The widespread adoption of mechatronics demonstrates its value in simplifying tasks, increasing reliability, and supporting innovation across industries. The future of mechatronics is bright, with advancements in sensors, control units, and actuators driving innovation. Emerging technologies such as artificial intelligence and the Internet of Things are expanding the capabilities of mechatronic systems. Automation will continue to transform industries, making devices smarter, more efficient, and adaptable. Mechatronics will play a key role in shaping the next generation of intelligent systems. While Mechatronics offers many benefits, it also presents challenges such as high initial costs, multidisciplinary expertise requirements, and complexity in design and maintenance. Addressing these challenges requires investment in education, training, and research. As Mechatronics continues to evolve, overcoming these obstacles will be essential for maximizing its potential and ensuring successful implementation in various fields. Education in mechatronics is crucial for developing skilled professionals capable of designing, implementing, and maintaining advanced systems. Training programs and interdisciplinary courses provide knowledge in mechanics, electronics, computer science, and control engineering. Investing in education ensures a workforce ready to tackle the challenges and opportunities presented by mechatronics, supporting innovation and growth in the industry. Mechatronics contributes to sustainability by enabling efficient use of resources, reducing waste, and optimizing processes. Automated systems minimize energy consumption and improve product quality, supporting environmental goals. The integration of mechatronics in manufacturing, transportation, and other sectors promotes sustainable practices and helps address global challenges such as climate change and resource scarcity. Mechatronics is a multidisciplinary field that combines mechanics, electronics, computer technology, and control engineering to create intelligent and automated systems. Its applications span home appliances, automobiles, office equipment, entertainment, robotics, medical devices, and military technology. The advantages of mechatronics include automation, efficiency, flexibility, and reliability, while challenges involve cost and complexity. Understanding mechatronics is essential for embracing the future of engineering and innovation. Conclusion: mechatronics has transformed the way we design, build, and operate systems across industries. Its integration of mechanics, electronics, and computer technology enables smarter, more efficient, and reliable solutions. As technology advances, mechatronics will continue to drive innovation, shaping the future of automation and intelligent systems. Embracing mechatronics is key to unlocking new possibilities and achieving greater success in engineering and beyond.